Hello everyone. Thank you for joining in. My name is Arindam Rama and I'm presenting from the University of Auckland in New Zealand. The topic of my presentation is calculating target thresholds for the margin value method using computational tools. I'm working under the supervision of Dr. David Wynn, who is also the co-author of this paper. One of the central concepts used in this presentation is that of margins. So before we begin, I would like to give you a quick introduction on the topic. Margins are quite commonly used by design engineers for various purposes, and consequently, there are quite a few definitions of margins which can be found in literature. Some researchers introduce margins as change absorbers, some relate margins in terms of adaptability, and some say that they emerge as a byproduct of suboptimization. What's common to all these definitions is that they are basically the difference between the ideal and the actual value of a parameter in a design. This leads into the problem. Margins have both desirable and undesirable effects. Desirable because they can be potential change absorbers and therefore can cater to the uncertainties involved in design. Whereas undesirable because of the obvious overspecification related problems such as unnecessary cost, excess material, etc. So the question therefore is how to create a balance between them. How to create a balance between having insufficient and excess margin, both of which have consequences. We have developed a method called the margin value method, which can be used to identify, localize, and size excess margins, and therefore help decide how to use these margins effectively to optimize the design. The method is based on the idea that decisions are what lead to these excesses in design, and finding out which decisions cause how much margin. The method is intended for an existing design where all the decisions have already been made and all the parameters and their values are known. In the approach, we calculate 4 metrics, results of which can be plotted on a graph. The vertical axis shows how much of the margin can be absorbed, and the horizontal axis shows how much the margin degrades or deteriorates the performance. The research paper in which we introduced the method, we had worked on a routine design problem of a conveyor belt design. All calculations in that design were based on algebraic relationships and did not have any complex calculations involved. In the paper submitted to this conference, we therefore are demonstrating an additional insight through an example of a flanged coupling, where finite element analysis is required in the calculations and not just simple hand calculations. As the method suggests, we create a design process model, then a margin analysis network, which leads to the calculation of the 4 metrics. In this particular case, we have used a topology optimization algorithm to optimize the geometry, thereby figuring out the margin in that particular component. The resulting graph is shown on the right-hand bottom corner of the screen. There are 3 points where margins were found. Just to give you an idea of how the results of a realistic design would look like, these were the margin analysis network on your left and the margin value plot of the conveyor design on your right. This case had 9 places where margins were found, some of which could be optimized. To conclude, this paper adds insight to the margin value method by showing how it can be applied in situations where necessary threshold values cannot be accurately expressed using algebraic expressions. It suggests how the margin value method could help to identify opportunities to improve design performance using additive manufacture of selected parts. It could perhaps be used in the field of design for additive manufacturing. Obviously, there are quite a few challenges, one of them being that the resultant geometry of such optimizations are usually complex and may not be practical to manufacture. The margin value method also calls for calculations to be repeated, which means finite element analysis must be run multiple times, making the process computationally intensive. And we have so far not considered the errors emanating from the algorithms themselves. In the future, we aim to relax these assumptions. More on these in a recently published research paper, which goes into much detail about the method with a more detailed example of the conveyor belt design. Thank you.